Hey everybody, welcome to my talk. I'm Shashank at AWS, and in this talk, we'll be talking about how you can accelerate your deep learning environments, custom environments on AWS. So, if there are two things I want you to take away from this session, the first thing is how you can build and share custom machine learning environments, and second, how you can scale these environments in the cloud. Now, let's talk about what a custom machine learning environment is. Now, if you're a developer or a data scientist, you're already familiar with working with Amazon EC2 instances or working with your machine learning training workloads right on your laptop or computer. And the workload looks something like this. You really need three key ingredients. The first, you want access to compute. And compute is basically your CPUs and GPUs or other accelerators that you need in order to train your models. And you also need access to storage because you need access to data sets, but also a place to store your training metadata and other data that you generate as part of the machine learning training process. And you also need access to software, and these are typically your machine learning frameworks like TensorFlow, PyTorch, but also proprietary libraries or other libraries that you develop as part of your machine learning process. Now, every machine learning development environment is different, and you may be building your custom machine learning environments by using your own custom proprietary libraries, which means that it's important to be able to have these environments and be able to scale these environments in the cloud as you go through your machine learning journey. Now, some of the benefits of this very simple setup is that it sort of mimics your local development environment. You have access to a Jupyter notebook that's running on an EC2 server, and you can train and test and prototype your models. And there are no clusters to manage. You can get up to 8 GPUs per instance on an EC2 instance. You also don't have to worry about data movement because you get up to 16 terabytes of local storage on an EC2 instance, and you get access to optimized ML frameworks with AWS Deep Learning AMI. Now, if you're not familiar with deep learning AMI, the deep learning machine image that are available on AWS for EC2 instances have all the latest machine learning frameworks from your TensorFlow, PyTorch, MXNet, and many others. And these are highly optimized and tested for AWS instances, such as your compute instances with the C instances and the P instances that you use for training models. And it also includes all the libraries from your CPU libraries and GPU libraries and make sure that they all work together well, which can be a challenge, as we'll see in a moment. And you get access to your deep learning base AMI, which just includes NVIDIA drivers, so you can build your custom environment on top of that, or you can get access to all the optimized frameworks, so you can just get started with these frameworks. Now, now let's take a look at a demo of how this experience works. So let's take a look at how you can connect to a EC2 instance and run or set up your custom machine learning environment. What I have here is your familiar Jupyter Notebook interface. While you may think this looks like a Jupyter Notebook server running on my laptop, it's actually running on Amazon EC2 instance. If I head over to the EC2 management console, you'll see here that I have an Amazon EC2 instance with the deep learning AMI, and this is a GPU instance. So I can now pull up a Jupyter Notebook interface right here on my laptop, which on the back end is connected to the EC2 instance. So I can run code that can take advantage of different GPU instance types or different CPU instance types. So there are many different ways to spin up an EC2 instance. You can do it through console or through the CLI. And once you have the instance set up, you can SSH to this instance like what I've done here and run my Jupyter server just by running the command Jupyter Lab. And I also want to set up a tunnel, and it's easy to do, just a single line of code that will allow me to access this Jupyter Notebook server running on Amazon EC2 instance. Now, one of the advantages of using deep learning AMI is that I can I get all these pre-configured deep learning frameworks that's optimized for AWS infrastructure. So you get all these popular deep learning frameworks, and you can just activate one of these and start using them. The way I like to use it is through the Jupyter Notebook by selecting the environment and choosing the one of the pre-configured Conda environments here. So I can quickly, let's go ahead and run this cell. And this is your familiar Jupyter Notebook interface. It's just that the backend is an Amazon EC2 instance rather than running it on your laptop. So this is your vanilla TensorFlow training script. I run this and you can see that it's starting to train, and this is a GPU instance. So what you can do is you can take a look at GPU utilization if you want to, and you see here that I have some GPU utilization hovering between 60 to 80%. Okay, so this is great. It's a great setup to build your custom setups, and you can install whatever libraries you want on top of this. But there are some challenges. While the simplicity makes it very attractive, there are some challenges with this setup. So let's go back to our slide presentation and take a look at what these challenges are. Okay, in this demo, we saw how you could access your EC2 instance on a Jupyter Notebook server and train your models and prototype. There are some challenges with this approach. Mainly three challenges I'll mention. First, it can be difficult to reproduce this environment. Let's say you built your custom environment on EC2 and you want to be able to share some of your training code with a colleague in order to be able to reproduce a problem or reproduce some results. Now, this can be challenging if you've really customized your environment. You've installed custom libraries, and if your destination instance or computer where your colleague is going to run it doesn't have the same set of software, then they may not be able to reproduce. Second, if you're working with a team and if every member uses a dedicated EC2 instance, you're not fully utilizing the available resources very well for two reasons. One, everyone's using a dedicated instance, so you're not sharing resources. And two, when you're developing, you're prototyping and testing, you don't really need access to a GPU. You want access to a GPU when you're actually doing the training. So when you're prototyping and testing, you're probably fine with a CPU instance. So your resource not fully utilized if you're always running on a GPU instance. And third, it can be difficult to scale. Now, it's easy to set up a single EC2 instance. The moment you add multiple instances, you have to figure out networking and how to distribute training across all these different instance types. Now, one of the reasons it is so difficult, specifically for machine learning, to be able to share your environment is that a machine learning stack, unlike many other applications, is very, very complex. Let's say you're a developer, you've written your code, and this is your development system on the left, and you want to share this piece of code with a colleague or a deployment team in order to be able to reproduce this code. So the expectation is that you give this code and they run it and everything works well. But the reality is that the stack is very, very complex. There are framework versions that can be different. There are framework dependencies that can be different. There are CPU libraries that can be different. There are GPU libraries that can be different. All the way to the operating system could be very different from your development environment to your deployment or a collaborator's environment. So what ends up happening is you introduce these multiple points of failure. So it could fail in a number of these different places in your entire stack, which can lead to you not having a portable environment that's consistent and that's shareable with others, especially when you build a custom environment with your custom libraries. So one way to address this problem is to use containers. Now, if you're thinking, hey, I'm not a DevOps person, I'm a data scientist or a developer, I don't want to deal with containers. Let's talk about why containers are important, because I'm with you on this. And I went along this journey to figure out why containers are very important for machine learning. So let's talk about why we need it before we talk about how containers work. Now, one of the benefits of containers is that it can encapsulate all these dependencies into a single, simple, lightweight package. So all these dependencies I mentioned can be encapsulated into this package, which can include not just your training code, but can also include your configuration and all the dependencies. Which way you can have a very guaranteed reproducible environment, especially when you have custom environments that you can share with others or scale on a cluster. Now, AWS also makes available deep learning containers, which includes optimized deep learning frameworks that are readily available for you to use. These are the same optimized frameworks that you find in the deep learning AMI, but they are now in dedicated container images that you can pull, build, test, prototype, extend it with your custom machine learning libraries and scale them, as we'll talk about through the later parts of this presentation. And you have access to not just TensorFlow, PyTorch, MXNet for many different versions, but also libraries like Hugging Face. So these are all available to you. And as again, they're fully tested and optimized for AWS. They include optimizations for storage, IO, and all the instance types that are available on AWS for you to do your training and prototyping. Now, one of the main benefits of containers, in my opinion, is that one, of course, it's lightweight and portable and consistent across where you're going to run it, but also that you can extend it. And if you have your custom code or custom libraries that you want to use to build your custom environment, you can start with an optimized deep learning framework, such as this TensorFlow framework shown here. You can start with the AWS deep learning containers that has all the optimized libraries, and you can extend it by adding your own custom code on top of this. And it works in a layer system, so you can keep adding your custom code on top of the container that you pull. And once you do that, you can save it in a registry. A registry is a location where you can save these images, and that way you can share it with others and use it to run it on a cluster where you can be confident that your environment is reproducible. Now, once you save this in a registry, others can get access to this, or you can choose who can get access to this. You can share it with a collaborator, and you can be guaranteed that they can reproduce your results, unlike previously where you would have shared a training script perhaps. With this, that you're sharing your entire environment, custom environment, with your custom libraries and custom scripts, so it's guaranteed to run on their environment. And you can also use this mechanism to scale on a cluster, as we'll talk about in the upcoming slides. Before we do that, let's take a look at a demo of what this experience looks like for you. I know as a developer data scientist, containers may not be the first thing that you're familiar with, but let's take a look at how simple and easy it is to get started with an AWS deep learning container, extend it, and push it to a registry with very few lines of code, so you can then use that to scale or share with others. In this demo, we'll take a look at how you can build custom containers by starting with the AWS deep learning containers. As I mentioned in the slide, AWS provides deep learning containers. You have containers for TensorFlow, PyTorch, MXNet, and others, with support for CPU and GPUs and different Python versions, and also for training and inference. So you can pull these containers as a starting point, use them as it is to run your training script, or extend them for your workflow. So let's take an example of how that works. So the first thing you want to do is log into this container registry, and these instructions are also in the GitHub page I provided. So once you log in, you're now able to pull containers from the AWS deep learning container registry. So to pull a container, you use a command docker pull, and when you run this, it'll pull the container. I already have this container, and it's confirming container image, and it's confirming that I have the latest version of it. I can also take a look at all the other container images that I have already on this system. So you'll see here I have some custom images, but also other TensorFlow images that I've pulled in the past. Now let's take a look at how you can extend these container images to include your custom code. So to do that, the first thing you need to do is write a Docker file. A Docker file is essentially instructions to Docker on how to build your custom container. So we start from the AWS deep learning container. This is a TensorFlow container, and you'll see here I start from this as a base container. I then copy a certain training script into this container. So I have this TensorFlow Cypher training script. And finally, I say that the entry point is Python and this training script, which means when I execute the container, I'll start training. In between, you can add custom libraries here. You can add custom libraries that you can include to personalize or customize your development environment or training environment. Once you push this, once you have this Docker file written down, you can now build this container and push it to a container registry. So to do that, First thing we'll do is define what we want to call our registry. I call it EKS ML containers. And then I use the AWS create repository to create the container repository. I see an error here because my repository already exists. I'll show you in a moment. After that, you build it using the build command, and then you use the push command to push it to the container registry. And you'll see here that all the layers, a container is built of layers, and all the layers have been pushed. Now let's go to Amazon ECR, and here you will see that this is my repository, EKS ML containers, and here are my two container images that I pushed to this registry. So with that, we just to quickly recap, we saw how you can extend custom containers and push it to a registry, which you can now share with other colleagues or collaborators, but also use them to scale on a cluster using Kubernetes or SageMaker, as we'll see in subsequent demos. Okay, so hopefully from the demo, you were able to appreciate the challenges that it can alleviate, such as creating this reproducible environment. But there's still two other challenges I mentioned that you want to address when you have these custom environments. First, as I mentioned, is resource utilization, being able to reuse shared resources across different users, but also being able to decouple maybe your development and your training compute instances, and also scaling without having to manage all these infrastructure by you automatically, as you would have done with a single EC2 instance, which is easy, but managing multiple can be challenging. So the broader question then becomes, how do you go from this model that you see here with a developer or data scientist working with a single EC2 instance to a model where you have multiple users in your team, perhaps sharing a set of infrastructure to increase utilization and to be able to scale your training or prototyping or experimentation? To answer this question, let's take a look at the fundamental building blocks, if you will, of typical machine learning infrastructure. So you have your compute, which is your Amazon EC2 instances. These are your CPU and GPU instances, but also the upcoming instances like Intel's Habana Gaudi and AWS Trainium that was recently announced. So these are all your compute instances. Now, this is where your software runs. Now you also need a place to store your software, and this is where the container registry comes into picture, which I mentioned earlier. So you build your custom environment, you push it to this container registry, and so you have access to your registry, which is sort of like an app store with your applications, and then your compute infrastructure where it runs. So what you need is something in between that can manage this for you. So you need a management layer that can take your software from the registry and run this on the infrastructure below. So be able to schedule your jobs on different EC2 instances and be able to scale them. One such solution is Kubernetes. I showed you Kubernetes and ECS. They are both services that have similar objectives. And one such open source software is Kubernetes. And Kubernetes, here's how Kubernetes works. So you as a developer, data scientist, want to be able to scale your training or host models on a cluster like this. So you're on the left here and you have this compute cluster on the right. So with Kubernetes, you can specify what your intended desired state is, and it will then take care of the infrastructure for you. It'll take care that it pulls the right software that you mentioned, could be a training job, and schedules this on one of the free resources in your cluster. So think of Kubernetes as an operating system for your cluster. Just like how when you run an application on your laptop, you don't think about how the operating system is doing threading and figuring out system memory and all that, right? It automatically manages for you. And Kubernetes orchestrates your training on a cluster by managing all the infrastructure related details. So you as a developer data scientist don't have to do that. And some of the benefits, of course, are that it simplifies training on a cluster. You get better utilization of resources because you're now sharing these pooled resources by multiple users, and it's easy to scale with Kubernetes and also add more resources or reduce resources in an elastic way. A typical Kubernetes-based machine learning workflow would look something like this. Again, Kubernetes wasn't built to be ML friendly. ML wasn't built with machine learning in mind, so it can feel a little counterintuitive to some people the way it works. But some of its benefits far outweigh sort of the initial learning curve of using it. So as a Kubernetes a user, you would write your specification on what job you want to run, how much resources you want, and then you build a custom container with your machine learning environment and your code, and you push it to Amazon ECR, which, as we saw in the demo. And after that, you tell Kubernetes to run this on a specified number of resources, and it can copy data set from Amazon S3 or EFS or FSX for Lustre or other file system and initiate your training. Let's take a quick look at what this demo looks like. We'll submit a job with the container we already pushed to ECR and take a look at how this training works. In this demo, we'll take a look at how you can submit training jobs to Kubernetes. Now, I've already set up a Kubernetes cluster, and I can use a Kubernetes CLI kubectl and say get nodes. Nodes are basically your EC2 instances that can take in workload and execute workload. So I have two nodes on this cluster. Now, when I submit a training job to a Kubernetes cluster, it can go ahead and provision the training on any one of these. Now I have two nodes, I could have 100 nodes or 1,000 nodes, could be a mixture of CPU and GPU nodes and so on. Now, one of the things you want to do before you submit a training job to Kubernetes, write a specification file. So basically this specification file says, I want to run a batch job. A batch job is a job that runs to completion versus microservice kind of a job which runs forever. And this batch job is very simple. All I'm saying is I want to run this specific container. This is the container that we built and pushed to the ECR registry. So I want to run this container, and this is as I showed earlier, this is the same container that we pushed to the ECR in the previous demo. So once I have this specification file written down, I can run a command like kubectl apply -f and provide the name of the specification file, EKS training job .yaml. Okay, so what Kubernetes did now is submitted this batch job, as you see here, and you can always take a look at the progress of this job. So I can say kube control describe jobs, and you can see that I have a pod created. A pod basically is provisioned onto that, which is a container that's provisioned onto the node. I can also say kubectl logs and mention the pod name, and I can take a look at the log of the container that's running out of instance, and you can see that it has initiated training. Now you will agree with me that the Kubernetes experience is not ideal for a developer or a data scientist, but nevertheless it's a very powerful tool that lets you improve utilization by sharing resources across different number of instances and different number of users. So with that, let's get back to our presentation. Okay, so that was the Kubernetes experience, right? You saw how it was, what the experience looked like to submit a training job to Kubernetes, monitor the results, and so on. But you may have noticed now that Kubernetes is not really a machine learning engineer focused solution. It's not data scientist friendly because you have to work with YAML specification files. There isn't a Jupyter experience, and there aren't many machine learning specific capabilities such as workflow management and pipelines and other capabilities that you expect, such as hyperparameter tuning and model hosting and all that. You can do all of these things, but it's just not. It just wasn't designed to do this as its primary objective. And of course, the developer experience is not something you're familiar with, having to write these specification files and apply them. Well, the community took notice, of course, and they started developing a layer on top of Kubernetes called Kubeflow. Now, Kubeflow aimed to do exactly this. It aimed to introduce all these capabilities that are machine learning specific, including pipelines and workflow management and model hosting capabilities, hosting Jupyter Notebook server. All these capabilities were introduced using Kubeflow that runs on top of Kubernetes. And on AWS, you can simply spin up a Amazon EKS cluster with a single line of code using the EKSCTL command line. And once you set up, you can set up Kubeflow on top of that. You get all the other benefits of Kubernetes using Kubeflow via Kubeflow. Okay, so far we've discussed compute, we've discussed where you store your custom environments in containers, and we spoke about the management layer. I mentioned ECS, but we also spoke about Amazon EKS as a way to do this. Now, in spite of Kubeflow, you still need some expertise in order to be able to set up a Kubernetes cluster, set up Kubeflow on top of it, set up Jupyter Notebook servers in order to be able to start using this for your data science workflow. Now, a lot of developers or data scientists don't want to go through all these steps. This is where fully managed services like Amazon SageMaker come into picture. So with Amazon SageMaker, you get all these machine learning capabilities within SageMaker for end-to-end machine learning workflow, all the way from dataset labeling to managing with Studio Notebook, which is an IDE for machine learning development, fully managed notebook instances as well. But you also get training capabilities, and you get hyperparameter tuning, model hosting, whole suite of capabilities with Amazon SageMaker. And the biggest advantage is that you don't actually manage the underlying infrastructure. If you want to train on a cluster of so many GPUs, you just specify and it's automatically provisioned and tear down once the job is done. So you get a fully managed experience with Amazon SageMaker. Now, if you build a custom machine learning container with your custom libraries and custom environment, there are a couple of ways to use SageMaker. Now, if your enhancements or if your changes are something that work with a deep learning framework already that's available in deep learning container, you can use this approach called script mode, where behind the scenes Amazon SageMaker will use the container, but you as a user don't have to worry about containers at all. You just provide your training script, and Amazon SageMaker will pull the right container, copy your training script, copy your data set, train on a specified number of compute instances, CPUs, GPUs, whatever you specify. But if you do want to work with your own custom container, you can also bring your own container. And the workflow is very similar. You just tell Amazon SageMaker that it should run this container on a specified number of CPUs or GPUs, and you'll go provision it, run the training, and then tear down tear down the cluster or tear down the instance once it is done training. So what you get is a fully managed experience. And let's take a look at both these approaches in a demo, and you'll see how this can really simplify a developer or data scientist workflow. In this demo, we'll take a look at how you can use Amazon SageMaker to do both script mode training as well as training with custom containers. So the first thing we'll do is load some necessary packages. After that, we'll upload our dataset to Amazon S3 because SageMaker expects your dataset to be in S3. And here's the workflow for script mode. So you'll bring in your training script. In this case, let's say you have a Cypher training script, and you'll write the SageMaker estimator function. Now, if you're using script mode, you don't have to worry about containers. SageMaker will automatically pull the relevant container and copy your training scripts into the container, and then provision a cluster or provision the number of resources you specify in your estimator function, and then copy your dataset from S3 and automatically tear down the instances after it's done training. And as far as the workflow is concerned, you specify your hyperparameters, and then you specify your estimator function. And in this estimator function, you'll specify where your training script is, how many instances you want to run this on, if it's a CPU instance, GPU instance, or what type of EC2 instance, framework version, which is TensorFlow 2.4, Python version, and others. And then you will call the fit function. And the fit function will go ahead and kickstart the SageMaker training job, and you can see the output here. You'll see some training progress here. Finally, the test results, test loss and accuracy. And at the end, you will see training seconds and billable seconds to be the same. Basically, this means that if you train on a GPU instance for 455 seconds, that's the duration you're charged for. Unlike if you were using Kubernetes, you're responsible for managing the data plane or the instances on which the training runs. So if the instance is running throughout the time the cluster has been running, then you're continuously being built for it. With SageMaker, you get a fully managed experience. You only pay for the exact duration of training. This lets you prototype quickly, try different instances just by changing a single variable here. Now, the workflow with custom container is very similar. You've already built and pushed a container to ECR. You just have to, in the estimator function, provide the location of the container. So we do that here in the estimator function. We just provide the custom container image, and behind the scenes, SageMaker will take care of pulling the container, provisioning the right resources such as this GPU resource, and once it's done training, it'll again tell you how many seconds it runs and what the billable seconds are. With that quick demo, let's head back to our slides. All right. So in this demo, we saw how you can use SageMaker to do both the bring your own script as well as bring your own custom container. Now, Kubernetes and SageMaker are two separate services, but you can actually use them together. So with there are some organizations, some teams that prefer using Kubernetes because they have a lot of workflows already set up on Kubernetes, on Amazon EKS, and they're already familiar with this process. But they still want to take advantage of some of the capabilities in Amazon SageMaker, because SageMaker has some additional capabilities such as fully managed training or hyperparameter tuning. That is something that they want to leverage or leverage as part of their Kubernetes workflow. So they can do that with these two projects that are also available. With SageMaker operators for Kubernetes, even if you're not using Kubeflow, just Kubernetes, you can submit jobs to SageMaker. And if you're using Kubeflow, and if you like using Kubeflow and you manage your machine learning pipelines using Kubeflow, there's also the SageMaker components for Kubeflow pipeline, where you can still set up your pipelines in Kubeflow, but each of the individual steps in the pipeline are actually SageMaker jobs. So you can be submitting hyperparameter tuning jobs to SageMaker. Now, think about this. The big advantage here is that while Amazon EKS is a fully managed service with a fully managed control plane, you're still managing the data plane, i.e., you're still managing the instances that Kubernetes cluster uses to run your compute. Now, if you want to be able to if you want to fully manage service with SageMaker, you don't actually manage those instances either. So in this sort of a workflow, you can actually have Kubernetes submit training jobs to SageMaker, where you can get burst capacity. For example, you can get a lot of compute instances for the duration of training, and it automatically shuts down. So this is another project if you want to be able to work with both. Now, let's recap all the things we discussed. Some of the challenges with custom machine learning environment can be easily addressed with containers. Machine learning stacks are very complex, but with containers, you get this lightweight portable environment. You get better resource utilization when you use a cluster, because you get sharing of resources across different users, and where you develop model can be different from where you actually train them on high performance GPU instances, for example. And it's easy to scale with both Kubernetes and SageMaker. People have different preferences. With SageMaker, you get a more fully managed experience, as we saw. If you want to learn more, I do have a introductory blog post on using containers for machine learning. And I'm not an ops person, and I started this journey a few years ago. And in this blog post, I try to explain or introduce containers from a machine learning point of view. So feel free to check out this. I also have other blog posts that cover a variety of different other topics in machine learning, from choosing the right GPUs, choosing right hardware for inference acceleration, managing experiments, debugging your models, distributed training, and others. So feel free to check out these blog posts as well. And of course, there's also training available to you. Feel free to go to the link here and you can check out all the training that's available on AWS. With that, I want to thank you for taking time to listen to me. My contact information is on screen. If you have questions, don't hesitate to reach out. Thank you for listening.